Hello, this is a talk about very big numbers. In this talk, I'll give you an introduction to big numbers, some of the context of using them, the names that they use, and a little brief introduction to one of the larger numbers in mathematics. Of course, we're constantly surrounded by big numbers, millions of views on YouTube, billions of pounds, and government budgets, or even trillions of dollars. But of course, we need to understand what these numbers mean. So here we go. Starting off with a small number, of course, 10. We understand what we mean by 10, and 100 is quite easy to understand, as is 1,000. And when we start getting up to 1,000,000, it can become a little bit harder to picture, let alone things like 1 billion or even 1 trillion. So in an attempt to give you a scale for that, think about it in terms of seconds. 10 seconds is very easy to picture. You can watch people run 100 meters in less than 10 seconds. We have 100 seconds. Well, it's 1 minute and 40 seconds. That's quite easy to understand. And of course, 1,000 seconds is 16 minutes and 40 seconds. Again, we can understand that quite easily. But when we get up into that larger scale of 1,000,000, 1,000,000 seconds suddenly becomes 11.5 days. And that's a bit harder to understand in terms of seconds. Now we move up to 1 billion. 1 billion seconds, 31.7 years. The scale is changing dramatically. And when we get up to 1 trillion seconds, we're at 31,710 years. This is an enormous amount, but it's a good scale of reference for when we move on to some of the more complicated areas later in this talk. So looking at some large numbers, in context, we have the area of Great Britain in kilometres squared, approximately 209,000. It's quite a few. Distance to the moon, 384,000. Chances of winning the UK National Lottery, 1 in 45 million. Which actually is a very big number. To put that in context, if we were to look at one combination of letters for the National Lottery every second, the time taken to see all of the different versions would be 520 days. It would take a very long time to see all of those. Some other large numbers we're used to seeing. Population of the Earth, roughly 7.5 billion at the moment. The age of the universe, current estimates put it at 13.7 billion years. And size of cloud storage on the internet, approximately 10 million petabytes, or 10 to the 13 gigabytes. Now, it's pretty hard to say whether that's an accurate estimate or not, and of course it's changing all of the time, so you may find slightly different numbers depending on where you look for that. Another one, quite interesting to see, the volume of the water on Earth in litres, 1.38 times 10 to the 21 litres, so 138, and then a lot of zeros after it. So again, we're looking at those larger numbers. It can be pretty hard to understand exactly what's going on there, thinking about that many litres, but putting it in terms of glasses of water, that is how many glasses of water it would be, 4.61 times 10 to the 21, with one glass being 200 mils. Now, I started thinking about that number and then thinking about, well, how many atoms are there in one glass of water? So if we take what that 200 milliliter glass of water and do the calculations, some friends who understand chemistry better than I do assure me that the number is approximately 4.62 times 10 to the 24, and the number is written there for you. To put that in context, that is larger than the number of glasses of water than there are on the Earth. More atoms in one glass than there are glasses on Earth. Quite an interesting number, that one. And numbers of atoms in the universe, the last of these we'll look at is approximately 10 to the 80, that number all the way written across there. How many atoms are in the universe? Absolutely huge number. So looking at one of those in particular, if we look at the size of cloud storage, which I believe is about 10 million petabytes, or 10, what's that? That's million, billion, trillion, 10 trillion gigabytes. We try and put that in context. The largest commonly available USB thumb drive is approximately 512 gigabytes. Yes, I know you can get bigger ones, but that's a sensible size to look at as the largest sensible one to get. So how many would we need if we were going to store the internet on USB thumb drives? Well, if you do the calculation, it's approximately 1.95 times 10 to the 10 of those. That's the size of that number. It's a very big number. You need a lot of them to store the internet. Obviously ignoring a lot of the logistics in downloading the internet. So let's do some calculations based on that number. Well, if we take the average USB thumb drive to be about 1 centimetre tall, 2 centimetres wide and about 6 centimetres deep, how long would that line of 1.95 times 10 to the 10 of them stretch? Well, if you put them next to each other, they would stretch to the moon, and back, and to the moon again. It's an enormously long line. So we can see how these big numbers can come up. Okay, more of a math style problem now for some large numbers. What if we had 10 people standing in a line? How many different ways could we arrange them? Well, this is quite easy to calculate. There would be 10 people we could choose for the first person in the line, 9 for the second, 8 for the third, and so on all the way down to 1. And this works out to be just over 3.5 million different ways of arranging 10 people standing in a line. I said we'd put this in context, so if we looked at one arrangement of people every second, it would take approximately 42 days to see all of them. Of course, we can't look at one per second. It would take a little bit longer than that to arrange them. So, carrying this on a bit further, instead of 10 people, what about if we had 500 people standing in a line? How many ways could we arrange them? Again, the calculation is quite simple. 500 choices for the first person, 499 for the second, and so on, all the way down to 1. When you do that question, you get that number, 1.22 times 10 to the 1,135. That's this number. That is an absolutely staggeringly huge number. With 10 people, 42 days. With that many people, if you looked at 1 per second, well, the age of the universe is roughly 4.32 times 10 to the 17 seconds. This is 10 to the 1135. Absolutely enormous. It would take many, many, many times the age of the universe to look at just 500 people standing in a line. Okay, so we've got a lot of big numbers, and we can look at these in a variety of different ways, and we can marvel at how big they are. However, we need to have a little bit of a think about some of the different numbers and the way we name them, because of course this large number that's on the screen is a very hard thing to name other than very, very big. If you ask most people what's the largest number they've heard of, if they have any background in maths, they may well say a googol. Well, a googol is 10 to the power of 100. This means 10 times 10 times 10, 100 times, and it looks like that. It's a very, very big number. And for reference, going back to the number of atoms in the universe being 10 to the 80, this is a number that is much bigger. This is a number that doesn't have an enormous amount of use in the real world. The proper name for it is 10 duotrigintillion, which is not quite as nice to say as googol. The name for googol was named in 1938 by a 9-year-old called Milton Sirota, although I may have pronounced that surname wrongly, who was the nephew of the mathematician Edward Kazner. When asked what he wanted to call this very big number that his uncle was working with, he said, let's call it a googol. He named it after this character, who's called Barney Google. This was a cartoon character at the time, 1938, and who he named it after. And of course the name Google has gone on for Google. Google the company is named after Google the number, as a suggestion of the amount of things that their search engine can find. Of course, they've spelt it slightly differently, though. So to put this in context, how big is a googol? Well, we talked about 10 to the 80 being the atoms in a universe. 10 to the 90 grains of sand would fit into the universe. 10 to the 90, so bigger than that. The smallest sensible measurement of length used by a physicist is called a Planck length, which multiplied in 3 dimensions is a Planck volume. And the universe is 10 to the 183. So there are more than one Googol Planck volumes in the universe, but there aren't many other things in the real world you can find. Going on from a googol, Edward Kazner asked his nephew what other numbers it would be sensible to name, and they talked about a Googolplex. Now, Googolplex is 10 to the power of a googol, which is 10 times 10 times 10 times 10, a googol times. That's that number at the top there. That's that many tens. An absolutely enormous number, ridiculous number, really. That's one definition. I prefer the definition given by the 9-year-old Milton Sirota, which was he said that a Googolplex was 1 followed by writing zeros until you got tired. I think it's a much nicer way of doing it, but Googolplex, 10 to the power of a Google. Okay, so now we need to talk about names of numbers a bit more, and we're going to talk specifically about this film, The Imitation Game. Worth watching, especially if you have an interest in maths or an interest in the history of the war, because of course this is concerning Alan Turing and the Enigma machine and a cinematic version of his story to crack the Enigma machine, a great coding problem. Now, the Enigma machine is a very complicated coding machine, and it can be set in many, many different ways. The actual number of different ways that you can set it up is that number there, extremely large. And because of this many different ways of setting it up, that is what caused the great problems when the Allied troops were trying to break the code. Now, in the film, to say this number, what they actually say is 159 million, which is good in one way, because it's an easy thing for the general public to understand. A million is a big number, and there's a million, so that's very big, but now there's a millions. But it's just not very satisfactory for how to name this number. For example, we don't call that 1,000,000. We certainly don't call that 1010. So we need a better numbering system. Now, we've already talked about a million, then a billion, then a trillion, and this is adding 3 zeros each time. But what happens when we go further? Well, most people aren't used to seeing these numbers themselves. We have, after trillion, quadrillion, then quintillion, sextillion, septillion, octillion, nonillion, decillion, and so on. And it keeps on going up like that. And there's lots more. However, this numbering system becomes a little bit clumsy after a while. And so there is an alternative way of naming numbers. There is a study in maths called Googology. And this is something that not too many people seem to know much about. But this is the study of very, very large numbers. Googology has its own website, googology.wikia.com. On this website are a variety of different numbers and their uses. Now, all of these numbers have been used in mathematical problems. So all of these numbers have had their uses. They've either been involved in explaining other problems in maths or in solving various problems. But the good thing is that the mathematician who comes up with a number is allowed to name it. And as long as it has a proper use, you can name a number. So, of course, you could make up your own one as long as you can define it. And it's different from all of the others. And things like a Google +1 are not allowed. So what I've got now is a series of names of some of these other numbers. And some of them are quite fun. So you get things like a millillion, a Google gong, and a Googolplex. And of course, they're all named in fun ways, and some of them get quite silly, really. So we have the Google Bang, the Googolplex, Googolplex, of course, the Godgala, Godgalagong, Grand Godgalagong, Auga, Bongulus, Bingulus, Bangulus, Beangulus, Enormaxil, Monster Giant, the Super Monster Giant, the Humongulus. One of my favourites next, the Great and Terrible Tethrathoth. Sounds like something out of Doctor Who. The Great Big Booah, the Wompogulus, the Yotossel, the Great Big Hoss, the Quadrunculus, the Gigantibixel, the Great Destruxel, the Good Goshometty, the Super Gongulus, the Bukuwaha, and the Quabinga Bukuwaha. But of course, my absolute favourite is the Mia Lokapua Umpa. Of course, they're all very, very silly names, but they have all been used in mathematical problems. So if you want to have some fun, make up your own number, give it a silly name, call it whatever you want. Okay, so now we're going to move on to one of the sort of more famous large numbers. We're, of course, talking about Graham's number. Graham's number was created by Ron Graham in 1971. It was the largest number ever used to prove a mathematical theorem when created. It's quite a complicated problem. It's to do with the colorings of edges and parts of squares in multiple dimensions. It's a very complicated problem. For the moment, we're just going to think about it that way. There are plenty of resources available to find out exactly what the problem is if you want to. It has since been exceeded. There are now larger numbers used in mathematical problems. But this was the biggest at the time in 1971. We don't know its starting number. It's a very big number, it's very hard to work out. We do, however, know some of the last digits, and the last 20 digits are given for you there. It's a very complicated one. In order to be able to express this number, standard numbers don't make sense anymore. So we use arrow notation to express it, and I'm going to attempt to explain what arrow notation is. So for arrow notation, we use arrows, literal arrows. I'm going to call them up. In this case, that's an up arrow, A up B. And what that means simply is A to the power of B. And just to remind you, that's A times A times A times A, where A is appearing B times. As an example, 3 up 3 is 3 to the power of 3, which is 3 times 3 times 3. The 3 is appearing 3 times, and we get 27. 3 up 4 would be 3 to the power 4. 3 times 3 times 3 times 3, the 3 is appearing 4 times, we get 81. So quite straightforward for single up arrows. We can extend the notation, though, to be up up. A up up B is A up A, etc., where the A is appearing B times. So 3 up 3 is 3 up 3 up 3 up. I think I said one too many ups then. And we can think of that as 3 up in brackets 3 up 3. So this is 3 to the power of 3 to the power of 3. Well, 3 to the power of 3 is 27, so this becomes 3 to the 27, which is 3 times 3 times 3 times 3, 27 times. And that works out to be just over 7 trillion. That is a very big number. So 3 up 3 is just 27. 3 up 3 is 7.5 trillion. It gets big very, very quickly. However, that is nothing at all. We go further. 3 up 3. That is 3 up brackets 3 up 3. Now the bit in the brackets is that 7 trillion number. So this is 3 up 7 trillion. What that means, 3 up, 3 up, 3 up, 3 up, 3 up, and so on, with there are 7.6 trillion threes in that line. Or to put it another way, 3 to the power of 3 to the power of 3 to the power of 3, where there are 7.6 trillion threes. Now to give you an idea of the scale of that, if each 3 in that tower was 1 centimetre tall, the tower of threes would stretch around the Earth 1,903 times. That's not the number, that's just the list of threes. To work out what that number is, it's that. That is ridiculous. That has 3.6 trillion digits as a number. That is enormous. Remember, there were 10 to the 80 atoms in the universe. This is 10 to the 3.6 trillion. This is what we call in maths ridiculous. Let's go further. 3 up 3. This is 3 triple up that ridiculous 3.6 trillion digit number, which is, of course, 3 up 3 up 3 up, etc., etc., but repeat that the ridiculous 3.6 trillion digit number of times. Or to put it another way, if we have 3 to the 27, that is how many threes we have in our tower. That number is how many threes we have in the next tower. That number is how many threes are in the next tower. And we keep going so that there's 7.6 trillion layers of that before we write it down. That is an absolutely insane number. Way beyond what we can possibly consider. 3 single up 3, that's fine, 27. 3 double up 3, pretty big. This is getting obscene now. There's our 3 up 3. There's our double up. There's our triple up, that ridiculous number with 3.6 trillion digits. The next one is absolutely insane. Just no way of understanding it. So what is Graham's number now that we've got our up arrow notation down? Well, G1 is that absolutely insane number. G2 is 3 and G1 amount of up arrows. So that number that we have absolutely no way of possibly comprehending, 3, 4 ups 3, is how many arrows there are in G2. Then we get G3, which has G2 amount of arrows. And then we get G4, which is the same thing. It's G3 amount of up arrows. Absolutely ridiculous. And we keep going. Graham's number is the 64th one in this series. Now, the strange thing about Graham's number, when he used it to work on his particular problem, he couldn't work out the solution to the problem that he was actually working out. But what he did say is the answer is definitely less than Graham's number. Okay, well, we know it's less than Graham's number. Still must be a pretty big number though, right? Well, the only other statement we know about it at the moment is that the actual answer is bigger than 12. Somewhere between 12 and G64 is the solution to that problem. I believe that the answer to the problem is suspected to be 13. However, nobody can prove it yet, and I think we're a very, very long way away from it. So large numbers, they can be named very stupidly, they can be named in a very fun way, or they can be used in these absolutely ridiculous problems. Hopefully that has given you a little introduction to some of the very big numbers that there are out there in the world. Thank you very much for listening.